In our next video in the geometry unit, we are going to look at shapes. We're going to look at triangles and then basically everything but triangles, polygons, and we're also going to begin to look at perimeter and circumference. In the first section on triangles, we are going to look at how to identify triangles by their sides and also by their angles, because we can talk about triangles a couple of different ways. Then we're going to look at how we know when triangles are congruent and when they are just similar and what the difference between those two things is. When they are similar, we'll look at how to find the missing side. So let's start with classifying triangles and just even what triangles are. So a triangle is going to be a three-sided closed object, and all of the angles inside of a triangle add up to 180 degrees. All the points where the line segments come together are called vertices. That's the plural of a vertex. So you can remember when we had an angle, where it met was called the vertex, and now we're just going to basically close up that angle, and then we're going to have two more, and so now we'll have three vertices. When we are talking about angles inside of the triangle, so you might remember that we named these points with capital letters, so let me make a little bit of a better triangle here, where I have triangle A, B, C. And I can talk about it as triangle ABC, and we name it using really talking about the angles. The angle, if you stand on the angle, if you imagine standing here on point A or vertex A and then looking across, that's going to be the side A. And then if you're standing on C and looking out, this would be side C, and then this would be side B, and the sides use lowercase letters. We can name triangles either by what their angle measurements are or how many sides are congruent, like what the measurement of their sides are. So if we're talking about by angles up here on the first row, if you have an acute triangle, that means all of the angles in here are acute. So all of these angles are less than 90 degrees. So it could be that like once 60 and then like one's 80 and one's 40, something like that. Or you can have just one 90-degree angle, and that's called a right triangle. And then these two could be like, I don't know, 50 and 40. They could be both 45. They could be 60 and 30, or something that adds, two things that add up to 90. Or you can have an obtuse triangle where there is one angle that's an obtuse angle, like say 120, and then these other two items would be whatever you need to add up to the 180. So like maybe I need 60 more degrees, so maybe one's a 40 and one's a 20, something like that. So you can name it by angles, or you can name it by congruent sides. So congruent in the world of geometry is just a fancy way to say equal. So if two sides are congruent, that means two sides are equal. The way we denote things being congruent in geometry is like with little bars or tick marks. So you can see that this has one little tick mark and this has one little tick mark. That means these two sides are congruent. They're the same side. And you'll see the same thing that happens here on these angles. That means this angle and this angle are the same. If you have one pair of sides, so two of the three sides of your triangle are the same, they're congruent, that's isosceles. The sides that are opposite those angles, remember if this was like angle A, this is side A, and if this is angle B, that this is side B. If the sides are congruent, their angles have to be congruent. If their angles are congruent, the sides across for them have to be congruent. So think about it as like you're opening up this space and you're sweeping this space. So that space that gets swept is going to be the same if the angles are the same. Now in this one, all of the sides have the same number of tick marks. So that means they're all the same. All the sides are the same, which means all the angles are the same. And if all the sides are the same, that's an equilateral triangle. Equi for equal, right? Lateral for the sides. It's also equiangular because all the angles are the same, but we call it an equilateral. If all the sides have different lengths, you can see this one has 1 tick mark, this has 2, this has 3. That means it's scaling. Everything's different. That also means all the angles are different. So this would have 1 little bow, this one would have 2, and then this one would have 3. And then you would know, oh, all the angles are different. If all the angles are different, then all the sides also have to be different. But doesn't matter how big or how small or how many number of sides are congruent or angles are congruent, those interior angles have to add up to 180 degrees. Now the sides of the triangles don't really have any special names except for one triangle, and that's the right angle triangle. Let me go back to that and clear out some of this mess. You can see that is the only one right here that has a fancy name, the hypotenuse. The side that is across from the 90-degree angle is called the hypotenuse. We call the other ones legs. The other ones, other triangles, their sides don't have fancy names. Only right triangle. Why? I don't know. I never bothered to look it up. I just was like, okay, that's the rule. That's what I'm going with. So since we know that all of the triangle angles, all 3 angles in every single triangle, just doesn't matter how big, how small, what the shape is, you know, like how many are equal, they all have to add up to 180. If I have expressions for the angles, I could do just like what we did before when we were looking at parallel lines and adjacent angles. I can say, oh, well, all of these things need to add up to 180. So x plus 17, and it doesn't matter the order, plus a 3x minus 62, plus just an x. This has to equal 180. So I'm going to distribute my little positive 1 that's out in front of my angles that we talked about. And so that's x plus 17 plus 3x minus 62 plus just an x. And we can combine these like terms. So I have all my x's, so here's an x, 3 more x's for 4 x's, and now I got 5 x's. And then I have $17, but I spent $62. So let's see, what is that? Negative $35? Sounds good. Wait a minute. Negative $45. Okay. That's equal to 180. So I have minus 45, so let's go ahead and add 45 to both sides. Plus 45 plus 45. That's going to give me a 5x equal to 225. And when I divide both sides by the 5, I've got x is equal to 45. But I'm not done yet, right? So x is equal to 45, but I don't have just x. I mean, this one does, but this is x plus 17. This is 3x minus 62. I need to take my x. I need to plug that into each expression so I can find out what the angle measures are. And now you can see this whole process written out much more neatly and see the expression that we subbed in. Of course, yep, that's a 45, but 45 plus 17 is a 62. 3 times 45 minus the 62, that's going to give me a 73. And I can check to make sure that all of this adds up to a 180 to make sure I did all my math correctly. So that's how every single one is going to work. Of course, the expressions will look different, but it's the same idea each time. You have 3 angles in every triangle. It has to add up to 180 degrees. If you have more than one triangle, how do you know if they're congruent or not? You'll need to, in this point, because this is not a geometry class, look for all of those tick marks and those markings. So you may have to kind of turn an object a little bit. Let me see if I can get this turned a little bit here so you can see what is going on. If I can get this to cooperate, let's get that. And I'm going to put this in here and try to get it to match. It's almost the same. Right, so if I have this here, you see how it's the same size. If I take it over to this one and give it a little spin and bring it over and line it up, those two are the exact same size. Now, I didn't really have to do all of that because it has the tick marks, right? You can see that these tick marks line up if you move it off to the side. So these two right here, BA and what's that, ED, those are corresponding sides. BC and FE, corresponding side. AC to DF, that's also a corresponding side. Corresponding parts of congruent triangles are congruent. So I know that BA has got to be the same as ED, and BC, that's the same as FE. All I need to do is turn it. Now, if it were geometry class, there's this whole big long process that you have to go through, but for us, all we're going to do is look at the different tick marks and see if we have the right combinations. There's a couple of different combinations that you can use to make sure that everything is indeed the same. So you might notice on this, we have these two sides and these two angles, but we don't have anything about this side, right? And we have nothing about this angle, but since we know these two are the same and that they have to add up to 180 degrees, it doesn't matter what this is. If that's X and that's also an X, and of course these are congruent, so that's X and X, this leftover Y, even though we don't know what it is, has to be the same on each one. And we know if your angle's the same, the side across from it has to be the same. So the fact that these both have to be the same angle measure means the side that opens up across from them also has to be the same. So you don't have to know every single piece. You just need to know enough pieces so that if you did have numbers and wanted to find the missing parts, you can do that. So there are a few different combinations that work. There is side, side, side. So if you know all three sides to one triangle are congruent to the other, then we know that the sides and the angles are related. And so if I know all the sides, I know all the angles. If you know a side, an angle in between, and then the next side, so something like this, side, angle, side, then I can use that to fill in the rest. And that's kind of what we had over here, right? We have really had angle, angle, side, but we have enough to fill that in there. We also have angle, side, angle. So if I have like this unknown angle, the bottom piece, and then another angle, like this, then I'll be able to fill in the top part of the triangle. Or you can have what we had on the last one, which is angle, angle, side. So like this, this, and then just one of those sides. But we had two on the last one. That's all we needed. Now these don't necessarily need to be the same. It could be two different angles in here, but we just need to have another triangle with the same markings, and then we know, oh, those two have to work. So it can be a little sneaky. So if you look inside of a rectangle, even though we haven't talked about those yet, you know you got basically two triangles stuck together, right? Like you see this triangle right here. And then we have this other lovely little triangle. Let's make him blue right here. And they're sharing that side. So that means it has to be equal. I mean, it's the same side, so the blue and the pink overlap. We have one side. So I either need two more sides, or I need a side and an angle, or two more angles. Well, I got an angle right here. I got this right angle and this right angle. And you can kind of see that fold line, right? So this would flop over right to this one. And so I have an angle, and then I have a side. So what I need is one more angle. So this is where these directions needed a little bit more for us to be able to say, oh, we know that this is this type of figure, and use angle, angle, side. These, maybe they meant them to be the same, but probably not. So I have this figure right here with this one, and then I have the two. I also know that I have these pair of parallel lines. So this dotted fold line is a transversal, which means I have alternate interiors right there. So now I got angle, angle, side. And I can prove that this pink triangle and the blue triangle are congruent. If there was more information in here, like maybe something about the fact that it was a rectangle, which would have been important, then we would have had all three sides, because we know opposite sides in our triangle are congruent. The directions leave a little bit to be desired, but you can see how that angle, angle, side would work. So you do those types of things when you are looking to see if two things are congruent. So all the angles are the same and all of the sides are exactly the same. Now in a similar triangle, you are taking something and kind of scaling it up and down. So, and actually we've done this a little bit in some of our videos. If I take this, just drag it out here, make a copy of it, and then squeeze it down, they're not really the same anymore, right? Like they are, but one's a lot bigger than the other because I just copied it and made it real small, or I could make another one and make it real big. But notice I grabbed from the side. So it's keeping that aspect ratio. I didn't take it from here and give it a little smush or go like this and make it small. I'm making sure that the sides are growing at the same rate, up and down and out, right? That is a similar figure. So same shape, just one's a whole lot bigger. You can think of it as a scaling factor, right? So if I take this and make one bigger, one smaller, then you can see how it would fold right on top of one another. So what that scaling factor is, it can vary, but it's getting both the length and the width at the same time. Now, the angle measurements are going to be the same, but the triangle, the shape, the sides are going to be different. If that happens, so something maybe like this, right? Right, there's this, both share that same angle, but it's like this triangle stops sooner than this one. So you'll wind up with these same angles, but in different areas. It looks something like this. So you can see that this is marked, this has a 2, this has 1, and then I get my 90-degree angle. So all my angles are the same. So if I know my angles are the same and it's there, these triangles are similar, then I can use proportions to find out what that scaling factor is. Now, some of them you can look at and you're like, oh, it's obviously this. So like 5 times 3 is 15. 3 times 9 is 15. So 4 times that, well, that's got to be 12. They're not all that obvious. So what you want to do, and there's a couple of different ways you can do this, but this is the way that I think that's easiest. I think about that corresponding parts of congruent triangles being congruent, kind of like that same idea. I say, oh, I'm looking for this side. This lines up with the 4. So the 4 lines up with the x, which means, let me use the 3. The 3 will line up with the 9. 3 lines up with the 9. Now notice I have my small triangle up top here, my large triangle down here. You can have large first and then small, but it has to be the same in both fractions. So if you go small to big, the next one's got to go small to big. Those are equal. Got to have the same. Now again, you might be able to see right away what's going on, but you might not. So what we'll do for these proportions is cross multiply. 4 times 9 is 36. And 3 times x, well, that's just 3x, 3 times some number. So 3 times what would give me 36? Divide both sides by 3. And there's your 12. That would have also worked with the 15 if you didn't want to use the 3 and the 9. Both would do the same thing. So it could be use the 3 and the 9 or use the 5 and the 15. I like to go small to big, but you can go big to small. It really doesn't matter. Totally fine. It just has to, it can't be what it can't be. What it can't be is that. You can't go small to big and then big to small. No, no. It has to be small to big, then small to big. Now, I could have said x to 4, 15 to 5. That's fine. Large to big. Large to small, large to small. But you can't change directions. The sneaky ones, I think, are the ones that kind of have this overlay. Because you have this little triangle right here, this little blue one that I'll fill in as best I can. And then the bigger one, let me see if I'll make him pink. Out like that. So if I say, well, what's x? I know that lines up with the 18. Well, x goes to 18, sure. But 5 does not go to 10. 5 goes to 15. right? Because 10 is just this little piece. And I need this whole side to make the big triangle. So they do that on purpose so that you get the wrong number. Just make sure that you're getting both of those pieces. And then you just do the same exact thing. 15 times x is 15x. Oh gosh, that's a 90. So what's that? 6. X is 6. So x is 6. Right? 5 to 15, right, times 3. Well, x, some number times 3 is 18. 6. And again, you can go a couple of different ways. Just make sure that you're using the sum of that side and not just the 10 or just the, well, just the 5 for the small one, but not just the 10 for the big one. 5 to x, 15 to 18. You can, or upside down, x to 5, 18 to 15. Either way is totally fine. Or this one was inside of the triangle, like this to this, and then this to this whole piece. Usually I go from the corresponding parts, but either way is totally fine. Well, all the other shapes, including circles, are made up of triangles. So once you get a triangle down and you get a whole bunch of them together, you get a whole bunch more shapes. Lots and lots of shapes. So many, we just go with poly, right? Poly means many, gon is the shape, right, that side. So we're going to be able to identify polygons, all these different shapes, by how many sides they have. And we're going to talk about largely regular polygons and what those characteristics are, but there are some ones that are special. And then we're going to look at how to find the perimeter and how to talk about the interior and exterior angles of these polygons. And then we're going to talk about circles, which is not a polygon, but still made up of triangles. Now, the area, which we'll talk about in another video, of all objects, including circles, is called area, but the perimeter of a circle is called a circumference. And then we'll look at some application problems. So we know triangle, we just talked about triangle, that's 3 sides. Quadrilateral 4, pentagon 5, hexagon 6, heptagon, sometimes they say septagon, like September, right? 7, octagon 8, and it keeps going. They all have names. After a while, we just call them like n-gons. Like, so a 20-sided figure would be a 20-gon, right? We just get lazy and call them that. Now, all of these are closed shapes. Polygon is a closed, 2-dimensional, so length times width. So we're not talking about 3D shapes, polygon, like boxes or anything like that. If you're a regular polygon, that means your sides all have equal lengths. So these are all pretty good examples, probably even this one. This is the only one that's not a great example of a regular polygon because that looks like a rectangle. So you would be talking about a square for a regular polygon. That is a quadrilateral or a rhombus, but we'll talk about that in a minute. Now, there are concave and convex. We're not going to worry about all of that concave polygon, convex polygons, but there are other types of like that, right? That technically that's got 1, 2, 3, 4, 5, but not really not a pentagon. So some special quadrilaterals, those are the ones that we'll really talk about the most and that you see the most, I think, minus like stop signs and things like that, are the 4-sided ones, which are quadrilateral. So we got, let's jump around. We talked about rectangles and squares. Now, all squares are rectangles. Not all rectangles are squares. So if you take this rectangle and smoosh him in so that all the sides are the same, then you are good to go, right? Then you got a square. But if they're not the same, right, so that these sides are clearly longer than that, then they're not all the same, so you can't be a square. If you take your rectangle and kind of like push them over a little bit, you get a parallelogram. So it's like a slanty triangle. A slanty rectangle. And a rhombus is like a square that got pushed over, and it's like a slanty square, right? It's just kind of pushed over a little bit. Then there's our friend the trapezoid. Now there's actually two types of trapezoids. This is an isosceles trapezoid. There's also a regular trapezoid that looks like this, that has these two 90-degree angles. But they're both trapezoids. They both have the same types of formulas. It's just with one, you have two sets of like a 90-degree right here instead of this slanty side that has that kind of full line. They all have their own formulas for area, but as far as perimeter, everybody kind of has the same type of formula because it is just add up around the edge, all around the outside. That's how you get a perimeter. That's all there is to it. So if I have this pentagon and it says, hey, I'm a regular pentagon, regular means that all the sides are the same. So this is 7, 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 right? They're all 7. And I got 5 of those sides. So I can just add 7 up 5 times. Or I could say 7 times 5. Either way is fine. Either way, you're going to get a perimeter. That's 35. Now, if this is centimeters, it stays centimeters. Perimeter is always going to be in the same dimension. So this is just still going to be like to the first power here. There's no counter or anything like that. If I wanted to find out what's going on with these angles on the inside here, I'm actually going to use triangles to help me out with that. So I can think about this 5-sided pentagon, right? This pentagon being made up by a bunch of kind of slanty triangles, right? So I could take this pentagon, actually let me take this one right here and pick my officially favorite vertex, and then I'm just going to connect a line from this vertex to all the other vertices. This one's already attached, so I'll do this one. Now I'll do this one. This one's already attached. There we go. I got 1, 2, 3 triangles. Every triangle has 180 degrees. So that means this is 180 times 3, which is a number that is now coming into my head right now, 540. And you could do that for every single one, but there's a pattern. 5 sides, 3 triangles. 1, 2, 3, 4, 5, 6, 7 sides. 1, 2, 3, 4, 5 triangles. It's always going to be n minus 2. So the sum of the angles is always going to be 180, and then the number of sides minus 2, right? Because remember, I didn't have to draw these two. So now if I want to find out what each one of these little angles is in here, I just have to divide by however many I had. So this was 540 divided by 5. 108. So each one of these angles right here would be 108 degrees. Let's look at another one. I have an octagon. So 8 sides. Well, I can do it the old-fashioned way, right, that we just looked at. Here's a point. I go 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, 6 triangles. And each triangle is 180 degrees. So that would be 0 first, and then an 8. And then carry the 4, so 1080, and then I could divide each one of those by an 8 to figure out what angle each angle is out on the side, right? So 180 times whatever it was, the 10,080, right? 10,080, and now I can just go ahead and divide that by 8, and I can get each one. Or I can kind of bypass that, do it this way, and use the formula up at the top. Well, if this is a 135 right here, if I were to extend this, I can find out what this is, because that's just a straight angle, right? That's got to add up to 180, right? This little pink piece plus the 135 has to add up to 180 because it's a straight angle. So then that's got to be 45 degrees on the outside there. That's that exterior angle. This one's a little bit shorter. You can just go ahead and take 360 and divide by the number of sides, and you'll jump right to that exterior angle. If I wanted to find the sum, let's see, if this one, I got 1, 2, 3, 4, 5. All I need is 360 divided by 5. So what's that, 72? And 72. Or you can find all the interior ones and find this measurement and subtract it out. Either way is totally fine. Well, it's a little bit different with a circle. So a circle, we call the perimeter a circumference. And its formula is much more unique because we don't have anything sharp here. So now technically this is all made up of like an infinite number of triangles. It just makes it really, really small triangles so that you can't see like that little edge there like that. With circles, you really only need to know one thing, either the radius or the diameter, which are related. So if you know one, you know both. Now the radius is from the center of the circle to the edge, and the diameter is from one edge to the other, but through the center. The radius is half of the diameter, so 2 radii. If I have 2 of these radiuses, right, 2 radii, that gives me 1 diameter. If I'm given the diameter, all I have to do is cut the diameter in half, and I get the radius. And if that's all you need to know. Now, you normally see for circumference 2 pi r. But pi d is the same thing because we know the radius is half of the diameter. All you're going to do is multiply by something called pi. So what is pi? Pi is the number of times that you need to take your diameter, so 2 radii, regardless of the size of the circle, and lay it along the edge to get halfway through the circle right here. Right, so that's 3.14. If you don't believe me, find anything circular in your house and find the radius and see how many times you need to wrap that radius around the circle. It's going to be 2 pi every single time. So either 3.14 diameters or 6.28 radii to get around the edge. So it's all about that radius. So let's say I have a circumference that has a diameter of 10. So this is the diameter straight across. I can use the diameter, 10 times 3.14, which is going to be our estimate. 4 pi, which is irrational and doesn't end and doesn't repeat, so we just use 3.14. You probably have a pi button on your calculator somewhere. And you just multiply. That's it. If they would have said, oh no, your radius is 5, then I would have said 2 times 5 and then times pi, and obviously would have gotten the same thing. So let's look at something that's a little bit more exciting. What if I have this window, and you can see that the window has a lot going on here. I have this rectangular piece, and then I have this half circle up here. And let's say I want to find out what I need to go around the edge, like this, or like that. Okay, so this part, and this part isn't too bad, right? I have the 6, I have a 4, there's my other side for my rectangle, so I have another 6. So we're up to 16 so far. It's this piece that's a problem. Well, that's the edge of the circle, so let me find out what the circumference is. Now, I only have half a circle, so I can find the whole circle and then say by half, or I can just say, well, I only have half, so I'll say half. Half of my circumference, which is pi times the diameter. Well, this diameter, that's the diameter right here, which is the other part, of that rectangle. So that has to be a 4. So 3.14 times 4, take half of that, that's going to be a 6.28. So how about 20, what's that, 22-ish, and depending where I want to round, 22.3. And that is going to be what I need to cork up or paint the trim or whatever it is, a cap, all around my window. And that is how you find perimeter and circumference.